speaker is Isabella, tracing the total gas in a sample of nearby clouds.
Okay, well, can you hear me? Maybe not so well. Okay, we'll try this way. Yeah. Well, thanks the organizers for a very, very nice meeting. I've been learning a lot at the back of the room. I wanted to move you up in energy a little bit and use cosmic rays and gamma rays in order to trace the interstellar medium and trace, that doesn't work. I'm stuck here. It's nice, but I would prefer if we have a few view graphs. It's okay. Yes, okay, thanks. Okay, so the idea is really to use two total gas tracers. On the one hand, you have the upper map is the gamma ray map by Fermi, and the lower map is the one that Marc-Antoine here has done for the optical depth of the dust using some millimeter plus IRS plus corrections for the temperature and spectrum. And as you can see right away is that there is a very common distribution, but the devil is in the details. If you divide one by the other, then you start to get into trouble because the upper map is convolved, the total gas is convolved by the cosmic ray distribution density, and the bottom map is convolved by the dust to gas mass ratio and the emissivity cross section. So that's what we're trying to disentangle, and not addressing the whole sky. I'm just about to concentrate on two regions, the Chamaeleon region, which has been recently published as a common Fermi plus Planck collaboration papers, never do that again. And the second one on a smaller club using the same data in the anti-center region. So the idea is try to disentangle what is partly H1, what is partly CO bright H2, and what is in between the dark gas, which I start to call dark neutral medium, because all we know about it, it could be optically thick H1 plus diffuse H2, and it's a mix of both for sure. But the problem is the unknown proportion of both. So the only thing we know is that it's supposed to be neutral. So dark neutral gas would be a more accurate description than CO dark H2, because that leaves out the H1, or optically thick H1, because that leaves out the diffuse H2. So just to convince you that gamma rays and dust can tell us about this dark neutral medium, here you have the Chamaeleon on the left, and if I had a pointer, it would be much easier, yes. The Chamaeleon on the left and the anti-center region on the right that we've been analyzing, and you subtract what is correlated with H1 and CO. Simply. So you have here the gamma rays minus H1 and CO and the dust, and sorry, we're not self-consistent, so now the dust is there and the gamma rays is at the bottom. But essentially, when you have red, you have positive residual, something that is shining over emissive in dust or over emissive in gamma rays, and there's a very good spatial correlation between the two. And the correlation tells you that there is some gas, no way that the cosmic rays could shine in gamma rays with the dust itself. So there is some gas which are picked up by the cosmic rays and which are picked up with the grains, and they jointly trace gas which is missed by the H1 and CO altogether. So in order to use the gamma rays, what we have to tell you is that we have to derive the gamma ray emissivity per H nucleon, and then we can translate our gamma ray maps into gas column densities. We've done the analysis using the H1 only with spin temperatures, which are not only optically thin H1, but some combinations. as best derived from the gamma rays. And what you see here is the distribution of gamma ray emissivity per nucleon. In other words, cosmic ray density, if you like. And the cosmic ray density we get in a sample of nearby clouds are very consistent within plus or minus 9% only. And Perseus is slightly off, but there's a technical problem with Perseus. We have a lot of crosstalk between the H1 and CO maps because it's a very small, compact cloud in terms of angular scale. So this could be really a technical deviation, measurement deviation, and not a cosmic ray density change. We'll check that. Anyway, so we believe we understand the cosmic ray density in the local interstellar medium, which for interstellar people is useful, is that it corresponds to something like 10 to the minus 17 per second in terms of cosmic ray ionization rate, and an energy density near 2 electron volts per cubic centimeter. And, but if you use Voyager plus our gamma ray measurements. But what is really important is, which I'm not showing here, is you can monitor the spectrum, the cosmic ray spectrum, through the different gas phases, from the diffuse H1, DNM to CO. And if there were problems like penetration or magnetic mirroring or other problems with the cosmic ray penetration to the dense H2 phases, we would have energy-dependent variations, which we monitor and we don't find. So in the local interstellar medium, we believe that there's a rather uniform, within plus or minus 10%, rate of cosmic rays, or flux of cosmic rays, which we can use now backward in order to trace the gas. So that's what I'm going to do. And I jointly trace the DNM gas by having this spatial correlation between the dust and the gamma rays, in addition to the H1 and CO expectation. So the pain is in coupling both analysis and getting rid of everything in gamma rays which is not emitted by gas. But you can do that, and here in the Chamaeleon you see the H1 map, you see the CO map, and you see all translated on the same color scale into NH column density, and the dark interface, H1, H2 interface. And as you can see, the interface surrounds very much the CO. It's a size, angular size, which is in between the very diffuse H1 and the more compact CO. And in terms of mass, then you have by far the mass in the H1, and that I agree with Fukui-san, and twice as much thick H1 plus diffuse H2 in the DNM than in the CO. That's for the Chamaeleon. If I show you the anticenter region, where we have 6 different clouds, you get the H1 is still very dominant, and then you get about the same amount of gas in the DNM and in the CO. But here we have the additional problem of having H2. And actually, we've just picked up this region in gamma rays for the first time. So we can also give you the column density in the H2. So the bottom line here is that those numbers, masses, scale more or less with the volume available. Because the H1 has a much larger volume, you finally pick up, even though you have low density, you finally pick up a much larger mass in the end. And I cannot accommodate a factor of 2. For all our H1 analysis, we assume any spin temperature from optically thin to 100K. In order to change the amount of NH1 after correction for the optical thickness. But there's no way I can double those numbers, because the cosmic ray spectrum we would measure in those clouds would violate what we measure near Earth for the very high energy cosmic rays, which have no problems entering the solar system. Okay, so what you can plot after is the column density fraction of the total in the H1, in the DNM, and in the CO phase, just to look at where the transition from H1 to H2 occurs. And so you see that the CO really kicks up around 10 to the 21st per square centimeter in total gas column density. On the bottom plot, and it dominates over CO bright H2, the DNM dominates over CO bright H2 all the way to this transition. And this is the CO dark H2 fraction. So now I have to assume what the dark gas is. And the lower and upper gray zones define a composition which would be anywhere between 50% H2 and 100% H2. So that gives you a flavor for what the impact of the composition would be. Actually, not much. And what you see is that the CO dark molecular cloud gas would just transition, really become CO bright very well above this transition of a few, let's say 2, 3, 10 to the 21st per square centimeter in total. What we have here is the histogram of fractions, total mass fraction of the clouds when you add the CO, the H1 and everything. And you see that Wolfire and collaborators predicted that that dark gas fraction should be in mass around 30%. Here, in fact, depending on the composition, you have the color coding is the composition of the DNM. You have a broad distribution. Stay tuned because we're adding 8 more clouds here soon, but basically it's a broad distribution. So you have clouds where the dark neutral phase is really not much more, like the prediction, but you have clouds which are really overwhelmed with this phase compared to the CO bright. In terms of not column density, but the CO dark gas fraction as a function of extinction, which we just heard in a previous talk, here you have a transition between 1 and 2 magnitude as the models would predict. So very nice. This is the Chamaeleon figure, and we have the same in the anti-center for different clouds. Okay, somebody told me about looking at the color of the light, but I don't see whether, oh, thank you, just in front. Not the ceiling would be nice. Anyway, so let me turn to CO now, to the infamous XCO ratio. So for the gamma ray people, it's NH2 divided by the integral line width, WCO. It's not the alpha that other people are using. From analytical calculations by Bell et al. Or from simulations by Bertram et al., it's expected that we have XCO that collapses, literally, once you enter some shielding, because here you're really photodissociated, and then you enter the CO bright zone, and then XCO is more or less constant, because you add more CO, you have more H2, and the two correlate nicely, but then it increases again because CO saturates. The lines are becoming optically thick, and so you don't integrate WCO as much as you do for NH2. And as you can see, it depends also on the fact that the cloud has some dynamics, and if it's virialized, it's falling well into its potential well, and so you have nice large densities, a good screening, and you get a lot of low values. While if you have an unbound cloud, then you photo-expose to the UV radiation a lot of the outskirts of the cloud, and therefore you have larger values on a larger fraction of the surface. So if you measure XCO as an average over a cloud, which is the only thing we do at the moment, what you have, the average here will be much lower than the average here. So we've used that trick to measure XCO and look at the distribution of XCO in gamma rays. So we have no H1 to NCO difficulties. The XCO measurements as a function of cloud, nearby clouds. And they are organized, for those at the back of the room, they are organized so that you have WCO here, the average CO or the average extinction, or you have the surface fraction of very dense, very bright CO versus faint CO, or you have the CO line width, which tend to be broader when it's optically thick. And we find a trend that the average is driven by the fact that when you have large outskirts with large XCO ratios or more compact clouds with lower XCO ratios, then you have a decline. The total mass seen in CO doesn't count, nor the velocity dispersion in the cloud. Only the geometry versus edges versus core CO counts. And that's what Min was saying, that the Perseus measurement we get in gamma rays is very low, as what she got in the, oops, I didn't see the light. Okay, so one word which is important is our measurements stand here, and if we compare to simulation work, we can see that generally all the simulations I've looked at severely underpredict the CO emission by a factor of 20, 30 to 40. So there's something we have to understand on the theory side. And to wrap up, so let me turn to the dust for just a second. And here you see the optical depth as measured from Planck as a function of the gamma ray column density, so no chemical correction XCO ratios, nothing. As you can see, we find strong deviations. The dust behaves linearly with respect to the gas up to a few times 10 to the 21st, and then it starts deviating. That's why we have systematically all the XCO ratios measured by dust, which are larger, sometimes by a factor of 2, above the gamma ray values. And the XCO, but okay, I'll come back. Just look at this plot. The change in dust opacity, tau over NH, so emission properties per grain, changes best with dust temperature. At low temperature, we get variations, nonlinear deviations by a factor of 3, 5, in some places up to 8. So this is very dangerous for tracing gas with dust. And it does not relate, I cannot show the plot here, but I can comment just the bottom line. It does not relate to an increased rate, heat rate, because the power radiated by the coal grains we've checked is rather on the low side because they're well into the CO, so the field, the ambient interstellar radiation field is attenuated. So the change is probably a change in the grain capacity to radiate. And so people have looked, some people here have looked at the distribution of, Kohler and collaborators have looked at the distribution of dust versus spectral changes with respect to the dust temperature and the emissivity, let's put it this way, as tau over NH. These are measurements based on gamma rays at low angular resolution. This is higher resolution measurements based on H1 plus CO plus the DNM from the gamma rays. But essentially what you see is that we have variations by a factor of 2 or 3 in the anti-center and very well organized in terms of spectral change, temperature change, and emissivity change. And so this is really useful to test against models now. This has not been done yet because that plot was produced last week. And so what we see is that probably there's mantle accretion on the grains, and that would occur in the DNM type of column densities, that they aggregate into fluffy aggregates more in the CO phase from our maps, and the extreme tau over NH opacities are due probably to ice coating, according to this model, in the very dense CO part. But in other words, because of that tau over NH variation as a function of where you are, how dense the gas is around, it is very difficult to use the dust as a gas tracer, total gas tracer. And the second problem here, and I'm done, sorry. Well, yes, is really that we have to understand it's not only a gas density problem. There are some CO clouds with the same CO intensity. Some have the dust opacity that flares much more than others. So there's something else than just gas density or aggregates or something.
Okay, if you have questions, I think you have to wait, talk to her at lunch because we're out of time for questions.
Sorry.
So we had to move on. Sorry.